Having seen a fair number of architectural and compiler techniques, let's review where we are. We have decided we are going to use registers to improve cache performance. But now the question is, how do we have these large number of registers? The more registers we access, the larger are the number of bits needed to encode them in the instruction. We can typically expose only 32 or in some rare cases 64 registers. For example, if we have two registers, we can call one of them 1 and the other 0. If we have 4 registers, we can call them 0, 1, 2 and 3. If we have 64 registers, we'll have to use a lot of bits to keep track of their names. What can we do about this? How can we encode 128 registers with a small number of bits less than 7? I guess you'll have to watch this lesson to find out how we solve this riddle. So students, in this lesson we are going to look at a very interesting way of addressing the number of registers that are exposed in embedded systems or embedded processors. We are going to look at a technique called differential register allocation, which will allow you to expose more registers to the compiler, and therefore we'll be able to generate better code. And so let us look at the motivation for this problem. So the number of registers that are exposed in embedded systems is many times very small in many of the ISAs, and that's because the operand field does not have too many bits available to encode so many registers. So if you consider, for example, 2 operands to be part of an instruction, which is very typical, and if you allocate 4 bits, then you can at most have 16 registers available which are exposed. So you'll have 4 bits for one operand field, 4 bits for another operand field. So 8 bits are already taken away, and if your instruction width is small, this is typically what you would do. So the register field constitutes a big portion of the total code size. Embedded instructions are typically very compact, 16-bit and so on, and so you can see that in ARM about 25% of the total code size is due to the register field. Even outside embedded systems, in older processors such as Alpha, which were really high performance processors, almost 28% of the total code size was due to register fields. Now you may say that don't expose so many registers, but keep the architected registers much higher and the ones which are exposed lower, and then do the renaming as we normally do, map the exposed registers onto the architected registers. What is architected registers? The total number of physical registers that are implemented are typically called as architected registers. So maybe one can show only 16 registers for 4-bit field, but we can have many more architected registers or implemented physical registers like 32 or 64 and so on. Well, in such cases, then you have to rely on renaming. And renaming is an act of mapping a exposed register to an architected register. It costs power, it costs hardware, and it is complex in terms of dependencies and so on. And therefore, it is not desirable in the embedded world because the processor has to be simple. So in other words, in embedded world, the exposed registers are pretty much equal to the physical registers that are available. And so in embedded world, typically the ISA imposes a bottleneck because of the width of operand fields. For example, thumb could have 16 registers, but at a time only 8 are exposed and no renaming is done. So it is the job of compiler or code generator to manage the residency of data in these registers. At one time you can only use 8, however. In SC1110, there are 16 registers again, 8 high registers and 8 low registers are exposed. And again, it's the job of a compiler to manage these registers. In other words, in the absence of renaming mechanisms, your choice is to expose only a part of the registers that are available and manage them, and then keep some data in unexposed registers, and this creates complications. So before we get into the details of the differential register allocation, now let us review some concepts through a quiz. In the following statements, select the reasons why exposing more addressable registers is desirable. Check all those statements which are true here with a check mark. The first statement is, for high register pressure regions, more registers will decrease the number of memory spills. The second statement is, fewer exposed registers will improve compiler optimizations. Please put a check mark against the statement which is true here. Go ahead and mark your answers now. So let us look at the statements now for the answers. So what is the reason for exposing more addressable registers? Why is it desirable? The first statement saying that for high register pressure regions, more registers will decrease the number of memory spills, and that is correct. Why is it so? Because in high register pressure regions, very rarely will be able to accommodate all the variables in registers. So there will be lots and lots of spills. However, if we increase the number of registers, we will be able to accommodate many more variables in registers, and therefore it will reduce the number of memory spills. So exposing more addressable registers really helps to reduce the spills. Now let us look at the second statement. Fewer exposed registers will improve compiler optimizations. This statement is obviously false. The reason, of course, is that fewer the exposed registers are, the more is going to be the spills, and the poor is going to be the code quality, and we are going to have lots and lots of load stores in such code, and they are going to result in more number of cycles and poor performance. Now let us look at the proposal that is on the table, which is to encode differences as a part of the operand field in an instruction. So the key idea is, instead of putting directly the register number, put a difference between the current register and the previous register that was accessed by the instructions, and just put this difference so that we can expose more registers by this particular mechanism. So let us look at it through a simple example. So what we have is, in our original ISA, we have 8 registers, R0 through R7, and we will definitely need 3 bits for encoding them, because we have to be able to address 8 registers there. However, if we try to encode the differences in a clever way, this example will show that we can reduce the number of bits from 3 to 2 through some interesting mechanism. So let's walk through this example. Here is a sequence of registers that are getting accessed, and if we encode them directly, then this is the number that we have to put in the operand field in a binary form. So if R3 is being used, then we'll have to put a number 3 in the operand field, and we'll need certain number of bits for encoding this. R4 similarly is the next register that is being accessed. We'll have to put number 4 in the operand field, and we'll need a certain number of bits for that. However, if we encode the difference, that is, we want to tell the compiler that the next register that is being computed now is going to be the difference between R4 and R3. So the difference will be 1. So we'll have to encode 1 as the operand field in this particular case. What is this 1 telling us? 1 is telling us how to compute the actual register number in this particular case by using the previous register number. That previous register number was R3, and if we add 1 to it, we get R4. That is why we are just specifying that just put the difference in the ISA, because we know which instruction was accessing the previous register, and by using the register number associated with it, we can actually get the register number for the current instruction. So that's the key idea here. In a similar way, if our next access was R7, we'll have to encode the number 7 in a direct encoding. Now you can see that the number 7 under binary encoding will need 3 bits to encode it, all of them being 1, 1, 1, 1. However, if we go for a difference-based encoding, we'll get 3 here, and we'll have to encode this particular difference by using the binary arithmetic, binary encoding, and number 3 can be encoded here, as you can see, using 2 bits. If we continue in a similar way, now if we have the next access as R1, we'll have to take a difference between 1 and 7 to encode that as a difference, and suddenly we'll get -6 as a difference. And if we try to encode -6, suddenly the number of bits that we need again explode. So in other words, just by taking the difference and directly putting the difference as a part of encoding, this particular scheme, although it works until here, it fails here. So differential encoding is a good idea, but when it comes to going from R7 to R1, we have a -6, and to encode that, again, the number of bits that are needed will be extremely high. We'll need a sign bit, and we'll need bits for encoding 6, and that scheme will not work, and it will need more than 3 bits. So we have to think of these differences and encode them in a slightly different way than just taking a direct difference between the successive accesses of registers. So the previous example showed us that differences are a great idea, and they work for when the differences are positive. However, when we go from a register which is accessed, which is at a high level, to a lower level register, the differences become negative, and that scheme does not work. The differential encoding does not work. So how do we then make the scheme work even for that kind of situation? So to get rid of this extra bit that we have, we must avoid the negatives. Like in previous example, -6 somehow should be avoided. And so what we do is we resort to modulo difference, and we'll do an example to illustrate this idea in the next slide. So this is a small trick. The modulo differences avoid the negative differences. And so what we do here is we have a modified modulo arithmetic which will get rid of these negative differences and make the scheme work for differential encoding. So now let us put in a formula of computing these modulo differences. So let us say we are going from a register access of Rm to Rn, and we want to encode this particular difference. So the first access is Rm, and the second access that is forthcoming is Rn, and we want to put this difference into an instruction which is going to compute Rn using the difference and then get the data from that register. So let's see how to compute this. So the way to compute this would be to take a difference of n minus m and take a modulo with regard to the number of registers n, and this function d is calculated as n minus m if n is greater than m. That means this register number is higher than that. It's a straight difference. Otherwise, this difference is modified in this particular way. If n is less than m, that is, if you are going from a register access which is high to a low, that is m greater than n, then we do a difference again n minus m, but we add total number of registers to that to get the difference. So what is reg n here? The reg n is the total number of registers that we are operating on. So for example, if we have 8 registers in the previous example, reg n here will be 8. So this allows us to compute the numbers, the differences, always as positive entities based on this, and use that difference to compute Rn from Rm. So now let us see how this will work. Again, going back to the same examples where we had 8 registers, and in the original scheme the registers were directly encoded as numbers from 0 to 7, and this needed 3 bits. So the difference that is shown here for this particular example, if we decide to encode the differences using the modulo differential now that we looked at in the last slide, the modulo distance from R1 to R4 will be 4 minus 1 because R4 is greater than R1, and that distance will be equal to 3. So again, we'll need 2 bits here to encode the difference for this particular example. Now let's revisit the problematic case which we had this -6 for the previous encoding. So what if we are going from R7 to R1? How to encode this difference? In the original scheme it will be -6, which will cost lots and lots of bits, including an extra sign bit. But in this particular case, the distance will be 2 here, because as you can see that it will be n minus m plus number of registers. So n here is 1, m here is 7, so n minus 1 m will be equal to -6, and add to that the total number of registers that we have 8, and that gives us this particular quantity, and that's why in this particular case the modulo distance is not -6, but is by adding 8, which is the number of registers to it, it is converted into a positive quantity, which is 2. So now 2 is encodable using again 2 bits here, and we don't need 3 bits for this, nor do we need a sign bit. So what is really this modulo difference? The modulo difference is really the number of hops from one register number to the other in the clockwise direction. As you can see here, from R1 to R4, the number of hops were equal to 3, and that was the modulo difference here. And in a similar way, from R7 to R1, it is again the number of hops in the clockwise direction which is happening. So what is really the differential encoding scheme that we are discussing here? The scheme involves encoding the modulo difference between the current register number and the previous register number, and use that as a way of accessing a register. In other words, in this scheme, we'll have to compute inside the instruction. When it executes, it will compute the actual register number by using the difference. And so why is this scheme better? Because it typically allows us to use less number of bits. Instead of using 3 bits for 8 registers, it will allow us to use only 2 bits. Or, looking at it in a slightly different way, if you had a certain number of bits available in the ISA, you can encode more number of registers using the same. For example, using 2 bits, we would have been able to encode 4 registers because 2 to the power 2 is equal to 4. But now you can see in this scheme, by using 2 bits, we are able to encode 8 registers, double the number of registers. Let us continue this example and see exactly how this helps us to encode more number of registers or use less number of bits. So if we have first access as R3 and second as R4, then we encode just a difference, 4 minus 3 mod 8, which happens to be 1. 1 can of course be encoded only by using 2 bits. If we keep going, if the next access happens to be R7, in normal scheme you would have used 3 bits here for encoding R7 directly, but in this scheme, since R7 is the next access that follows R4, we just encode the difference, which happens to be 3, and it just needs 2 bits to encode it. And finally, we rectified this particular problem of negative offsets and the negative differences. So if the next access happens to be R1, now in this particular modified encoding scheme, under modulo encoding, we just incur the difference as 2, and it just again needs 2 bits to encode it. So here is the next quiz, which is on differential encoding. Let us test our knowledge of how to encode the differences. So given 16 registers, determine the differential encoding. Please write the number in these boxes on the right hand side for these different registers. Please go ahead and mark your answers now. So the first answer is between R6 and R4. You can see that the difference is 4, because again it is because of the modulo and so on. And using our knowledge, you can see that this particular difference will be 4. Between R2 and R16, again the difference is 2. Remember how we go in that particular sense, using the previous modulo encoding scheme that we did and going around the clock cycle. And then finally, between R12 and R15, it should be fairly straightforward to see this particular difference, and these are the answers. So the differential encoding scheme allows us to save space by keeping the instructions more compact, or encode more number of registers by using these differential schemes, as was pointed out earlier. The same example now, let us compare the number of bits. R3 would have been directly encoded as 011, R4 would have been encoded as 100, and as you can see here, now we are encoding the difference 01, so 2 bits are sufficient here under the new scheme. Continuing the same process, if the next access is R7, we would have encoded it as 111 directly, but now we are encoding the difference between R4 and R7. The difference happens to be 7 minus 4 modulo 8, happens to be equal to 3, and therefore we have only 2 bits which we need as 11. Lastly, if the access was R1, we would have encoded it as 001, but instead of encoding it that way, now we encode the difference, and under this modified modulo arithmetic, the difference is 2 here, and that is encoded as 1 0. So if you focus on the total number of bits that are needed in the previous scheme, direct encoding needs 3 bits, here we need 2 bits. Now in this particular quiz, we are going to determine how it is justified to do the differential encoding. So having determined these differential ways of encoding versus direct encoding, please write this in terms of the number of bits that are needed here for each of these cases, and go ahead and write your answers here for this. So let us verify what is going on over here. So if we had to encode R6 here, then 6 that will be encoded as 0110, whereas the difference between 2 and 6 is 4, as we've seen earlier one, and so that will be encoded only in this particular way, 100. Next, if we were to go from R16 to R2, the R2 is encoded now as 0010 as the direct encoding, whereas in the difference encoding we need only 3 bits, and the difference is 2 in this particular case, which is encoded as 010. One of the things that you should notice here is I am showing this as 4 bits because in order to encode things as high as R15 and so on, the register numbers, we will need 4 bits in direct encoding, whereas all the differences are confined within 7, and that's why we will need only 3 bits here. So again, here if we have to encode R12, this is how we will do it. 1100 is the encoding for R12, and the one for going from R15 to R12, it is just equal to 3, and therefore we just have 011 over here. So you can see that the number of bits that are needed here is much lesser than the number of bits that are needed for direct encoding. Now, having proposed this scheme of differential modulo encoding, let us see if 2 bits are always sufficient to encode all possible differences for this example of 8 registers. Now we saw earlier through this example, for the register access sequence, R3 followed by R4 followed by R7 followed by R1. If we take the difference encoding approach, we get these as the differences 1, 3 and 2, and it is always possible to encode them through 2 bits. So now let's change this example, and if the first access happens to be R0 and the second happens to be R4, let us compute these differences now. That will be 4 minus 0 modulo 8, and the difference will happen to be 4. Now 4 cannot be encoded by using only 2 bits. You can see that 4 will need 3 bits, and therefore certain differences cannot be encoded now by just using 2 bits. So direct encoding needs 3 bits, and differential encoding in this particular examples also needs 3 bits. So where is the advantage? As you can see here, if you compare all different potential possibilities of encoding the differences, there are certain differences which will not be possible to encode using 2 bits, but a major number of those will be possible to encode using 2 bits. So what if case like this, how to deal with this, which need 3 bits? For this purpose, we'll introduce another instruction here. So the instruction that we are going to introduce is called as set last register. So whenever the difference is not encodable using 2 bits, for example in this particular case, we are going to insert this instruction which will directly set the register number to the one that we want, in this particular case 4. This set last register instruction is typically cheap because all it does is sets the current register number to whatever is given to it, and if we do it, we don't have to encode the difference between 0 and 4 here. If we set the current register number to 4, we decide to not encode this as a difference, and in such a case we just incur the cost of 2 bits for encoding the differences. So in other words, some registers, when they cannot be encoded, or some register sequences when they cannot be encoded as differences, are directly set by using set last register, and whenever they can be encoded using 2 bits, we'll go ahead and encode those as shown over here. So the solution that we are proposing here is insert set last register instruction so that the encoder assumes the previously accessed register is R4 and therefore the difference is 0, and such instructions therefore set the current register to the one that we want, and avoid differential encoding. And in such an example, again the 2 bits are sufficient. Whichever differences can be encoded by using 2 bits will be encoded using those, and others will be simply set last register instructions. So again, as one can see it, by using set last register instruction, the differences are kept encodable to again only 2 bits, which are sufficient. So students, we had seen how the differential encoding works and helps in case of reducing the number of bits in terms of the operand fields of instructions. But in order to use that, we need to do some interesting program analysis and transformations. So let us take a look at the issues that are involved in using this differential encoding in terms of register allocation. So one of the first issues that we are going to look at here is called as multiple path inconsistency. So what are multiple path inconsistencies? So the big issue that we are looking at here is different path at a join point where the control flow box merge could lead to different differences. So now let's look at an example of multiple path inconsistency that I mentioned in the last slide. So here is a control flow graph, and as you can see here, we have 2 paths to come to this is the join point that we are talking about here. We have 2 paths, one from this side, another from that side. Along this path, you can see that the last register that was accessed was R1. Along this path, however, the last register that was accessed was R2. And in the subsequent basic block, which is BB3 here, we are going to access register R2. So you can see that if we come via this path, we are going to use register R2 followed by R2. However, if we come via this path, we are going to follow register R1 followed by R2. And so the difference between the register numbers on this path, which is equal to 1, is different from the difference on this path, which is equal to 0. So these 2 different differences is called as multiple path inconsistency. Let us look at these differences in terms of our encoding scheme. So the difference coming from this particular path going to R2 is 2 minus 1 modulo number of registers, and that is equal to 1. The difference on this side is, however, 2 minus 2 modulo number of registers is equal to 0. And so that's how we have 2 different differences here. So how are we going to reconcile this? So we can't put a differential encoding instruction here and say let's use difference 1, because what if we had come via this path? So what we could do is maybe pick one of the paths which is more frequent here and do differential encoding on this path. Let's say if we decide to do the encoding for frequent path using instruction 1, what may happen is we will use this particular instruction to generate the register number. But if we come via this path, on the other hand, in the beginning of basic block 3, we can encode difference equal to 0 by putting set last register 2 as the instruction. So in this case, we can put a differential encoding from here. If we come, that works well. Otherwise, we will do a set register 2 and we will be setting the register correctly without using the same difference on this particular side. So in other words, we'll try to do a separation of the differential encoding. On one side, we'll put this instruction. On the other side, we'll just use differential encoding and so on. So now let us look at the role of the set last reg instruction. So here is a quiz. So is this instruction meant for loading a new value into the last register used? Or is this instruction being used for remembering a new register number as the last register used? Or is it being used as an alternative to a register move? Please go ahead and mark your answers now. And the only correct answer here is the second one. The set last register is to set up what was the last register that was getting used here. Remember, when we cannot encode certain large differences, we break them up. We introduce a set last register as the instruction, which will reset the last register number that was being used. And from there again, we can start using differential encoding. So it is not for loading a new value, or it's definitely not a register to register move as well. So now let us look at the hardware support for implementing this differential encoding. So in hardware, what we need to make sure is we are decoding these instructions and generating the right register numbers from the differences in the register fields. So for using the difference, what we do is we have a way of noting the last register number, and we use this difference and then restore or generate the register number by using the difference and the last register number. So what we do again, as I mentioned, is add difference to the last access register to get the current one. Let us look at how the differential encoding will be implemented in the hardware now. We have 8 registers, let's say from R0 to R7 in our machine, and now let us see how the register number is recovered by using the differential encoding. Let us assume that the last register accessed was 3 and the difference that was encoded was 1. So using the modulo arithmetic, we will add 3 to 1, take a modulo with respect to the number of registers, and we get 4 as the next register number to be used for holding the value. So the decoded register number here is 4. Another example, let's say the last register accessed was 4 and the difference that was encoded was 3. By doing the modulo arithmetic that we saw earlier, 4 plus 3, we recover 7. Modulo 7 is going to give us the number 7 here, so that will be the register number that we have recovered. Let us say now that the last register access was 7 and the difference was 2. Again, using the modulo arithmetic that we saw earlier, we add the difference 2 to 7 and do the modulo arithmetic, and that gives us register number 1 as the current register to be used here. So now let us see the hardware implementation of decoding in terms of the needs of different resources. So first of all, we need a narrow register to hold the last register accessed. Secondly, we need an adder, and we don't need a huge general purpose adder. We just need an adder for adding short integers. So typically, the differences could be in terms of short integers, and for 128 registers we could have as many as 7 bits in terms of encoding the differences, and such short adders could be implemented very fast in hardware. Moreover, decoding can be performed in parallel, so the instruction decode cycle itself, we can actually decode the operands. While the opcodes are getting decoded, we could also decode differential information about registers in terms of the operands and keep those registers ready to be clocked in the next cycle to get the data from. In addition to decoding the operands along with the opcode decode, another possibility is to in fact parallelize the decoding of different operand fields themselves. So for example, typically you have 2 register fields in an instruction and both are encoded as differences of some sorts. One could use the decoders in parallel to decode and get the current register number as shown in this example. Let's say the previous operand field was register 1 for one operand, the second one was register 3 for second operand, and let's say the difference that we have encoded is 3. We can use that to parallelly add and recover the current register numbers, number 4 as one of the operand registers and number 7 as the other operand register, and they can be done in parallel. So having seen 2 important issues, one is multipath inconsistency and the second is hardware support for differential encoding, now let us see how we can integrate this into a register allocator. So as you know, we have seen the register allocation, the way it occurs using many different techniques such as graph coloring, range splitting, and so on. And so the question is, can we use the same techniques just with this new encoding scheme, or do we need new techniques? And if we need to change a given technique, how do we do it? So the first route that we look at here is take an existing register allocation that is done based on direct encoding and then change that to differential remapping or differential encoding by using this new addressing scheme. So this is to leverage the existing robust register allocator that we have developed and just implement differential encoding and remapping on top of it. The second one is to actually modify a register allocator by building differential select mechanism inside the register allocator. What is a differential select mechanism? Remember that act of visiting the interference graph and pulling out nodes from it and putting it on stack? That is called as a select stage of a register allocator. And maybe the order in which these nodes go on stack could be different based on the differences. And then the third is most aggressive register allocator, which is an optimal register allocator, which is going to do what is called as coalescing that we saw earlier, merging two ranges to save register to register moves, and then do the differential select also as a part of this mechanism. So what is the goal here? By coalescing, as you can see here, we are reducing the potential register residencies of different ranges. That is, when two ranges are merged into one, we are effectually eliminating a register to register move, and therefore less amount of differential encoding will be needed here, because now there is one range which we don't need to put in two different registers. And then by doing so, it will enable more opportunities for using differential encoding across ranges, and therefore we can do that using differential select. So that is the third optimal register allocator that we took and modified using these two techniques. Please refer to the instructor's manual and learning guide for details. Refer to the paper which describes these techniques. So we are going to show you some details of how differential encoding really affects the representation of interference graph. And then we are also going to show you how we can use that representation to some extent to do a differential select. So as you know, the interference graph captures the fact that the two live ranges are overlapping at certain program point. What it does not capture is what order the registers are getting accessed here. So we build another representation here, which is called as adjacency graph, which captures the sequence of register accesses. So assume that the register allocation has been done now on this interference graph, and you are going from one register to the other in the next instruction using this. If you capture these register accesses from one instruction to the other and build that into a graph representation, that is the adjacency graph of the accesses. This representation is constructed along with the interference graph. Each register is a node here, and then there are undirected edges. There is also an edge weight associated between two nodes, which represent the frequency of adjacent register accesses. So if you are going from one node to the other and you are going it 4 times, that edge weight represents such a frequency in terms of the accesses from R1 to R2. Let us look at the notion of adjacency graph that we talked about in the last slide through a simple example. So what we have here is a sequence of virtual register accesses through different instructions, and we have V0 followed by V1. Then the next instruction is also using V1, let's say, and then the following access is V2. The one which is following that is V1 again, followed by V0 and V1. So these are the sequences of accesses of the registers. Let us see how we captured this sequence through this simple graph now. So first off, we have these different nodes representing different virtual registers. V0 is one, V1 is another one, and V2 is another one. And what we have is directed edges between them, which tell us the kind of differential encoding we'll need to go from one to the other. And we have color-coded them. So for example, we are going here from V0 to V1, and we are doing that twice because that occurs once here, and second time that occurs it here. So this transition V0 to V1 is now shown through a directed edge because we are going from V0 to a V1, and then the frequency of that is 2, one from here and another from here. So that is shown in this particular graph. Let us now take another transition and see how to represent it through this graph. So let's say we have V1 followed by V2. So we have this transition V1 going to V2. And let us see where all does it occur in this sequence. It occurs only once here, and that's why we have this edge from V1 to V2 with a frequency of 1. Now the frequency of V2 to V1 should be captured differently because the difference encoding that will be different than going from V1 to V2. This difference will be 1. That difference will be a different entity as per our modulo arithmetic, and that's why from V2 to V1 we have a separate notion of differential encoding, and that's why we have a separate edge here which is directed from V2 to V1. It is your exercise to find out what the difference will be from going to V2 to V1 using the modulo arithmetic that we have seen. Remember, in one case it will be positive 1 going in this direction. There will be something else in the other direction. That's why we have directed graph here. And then finally, we also have the V1 going to V0 is a different transition that occurs only once, and that's why we have a directed arrow from here to there with a frequency of 1. Now you might ask me, what else is there? You can see that certain differences which are equal to 0 are really not needed to be captured in this, because the last register that we access need not be modified there. So when the differences are 0, we don't need to really explicitly represent it in this way, because we don't have to represent it through a differential encoding. Now recall that we have these differential encodings that are present in this graph, adjacency graph that we saw earlier, and we have this frequency. And also recall that not all differences can be encoded under a fixed number of bits, because certain differences will need maybe 3 bits as the earlier example showed, and we had only 2 bits. So again, certain differences could not be captured by differential encoding. If we can capture a difference, we say that the edge is covered. So the modulo difference between the two end nodes can be encoded in such cases after register allocation. For example, we have a node here R1, and we have another node here R5, and we have a difference, of course, of 4 between the two, and we can encode that through 2-bit encoding of the differences. We'll say that this edge will be covered, and in such a case, we'll be able to carry out the register allocation with the existing registers under differential encoding. So as we know, some differences could not be encoded because they would need, let's say, 3 bits as we saw in earlier examples. And so some edges of this adjacency graph we will not be able to encode using differential encoding. So the weights of uncovered edges are the cost. That is, for those edges, we'll have to insert explicit set last reg instructions because we could not encode those differences. An example here is, let's say, in our case, there is a difference between two accesses, R1 and let's say R9, and the encoding needs here 3 bits, and we have only 2 available. So you can see that the difference is 8 here, and to represent it, we'll need 3 bits. We have only 2, we cannot represent this difference, and therefore such edge will not be covered, and we'll have to pay the price by putting a set last reg instruction here. What will it do? It will set the register number to R9, and will not be able to take advantage of differential encoding in such cases. Let us see what we saw in the last example a little bit more in details through another example. So let's say the number of registers that we have is 3, and so the largest difference could be equal to 2 that we plan to encode, and that means that we have a register width which is 1 bit wide. So again, we could have larger differences, but we decided to just keep 1 bit width to cover the difference maximum value equal to 2. So here is the virtual access sequence that we have for registers. V0 followed by V1 followed by V0 followed by V1. And after register allocation, let's say we got R1 followed by R0 followed by R1 followed by R0 as the physical registers. And now we have to encode the differences here using the bit width that we have decided to put in there for encoding differences. So what are we able to encode? The difference of certain values using 1 bit width, we are able to encode differences which are value equal to 0 and value equal to 1, but we are not able to encode certain other differences using the modular arithmetic. And so let us see what happens. So if we go through this scheme here, you can see that the difference of 2 is needed to encode R1 to R0 transition, and difference of 1 is needed to encode R0 to R1 transition. Again, let's go back to this thing that we saw here earlier some time back. This is my R0, this is my R1, this is my R2, and in order to encode the difference, we got to go clockwise in this particular way. And so to encode the difference, with the difference here is just 1. The difference between R1 to R0, however, is 1 and 2, so there are 2 hops that are needed. We can't encode a value of 2 using bit width of 1. So that is why we have to explicitly put a setreg instruction when we go from R1 to R0, because we could not encode the difference of 2 using 1 bit. And so we have an explicit instruction here, and in a similar way we have an explicit instruction here. However, from R0 to R1 the difference is equal to 1, and we are able to encode it using differential encoding of 1 bit. What we discussed in the last slide is shown here now through access graph. So we had an access graph between V0 and V1 with these frequencies shown because of the access transitions in the last slide. Now we have decided to allocate the register. So now let us look at the first technique that we have based on this abstraction of adjacency graph and the coverage thereof by using differential encoding. So the first technique is differential remapping. What is the key idea here? The key idea is to be able to assign registers to the nodes of this adjacency graph so that we can minimize the costs and maximize the edge weights. How do we realize this idea? We realize this idea by a technique called global remapping, or permutation of register numbers after the register allocation is done. So this is really a post-pass technique. What it means is you have actually given the register numbers to different values, the direct register numbers. Now after that you build this adjacency graph out of it and decide what to do with it so as to maximize the coverage. So many times we'll have to redo certain numbers, we'll have to remap the registers, use one register at a later point, another register at an earlier point, so that the sequence is kind of different, and using that you can maximize the coverage. That is the key idea here. So now let us take this example. There are 3 registers, R0, R1, R2, and the maximum difference could be there equal to 2. But we have decided to use only 1 bit which can encode a difference of 0 and difference of 1. So if the register access sequence is such that we have to go from R2 to R1 and from R1 to R0 with these frequencies, because we are able to capture only certain types of differences here, there will be a problem because of this, and let us see what we can do about it. So again, let us see now if we can encode these differences. And as you can see here, this is the difference of -1, this is another difference of -1, and that translates to the actual difference of +2 using modulo arithmetic. We have only 1 bit which can either represent 0 or 1. We cannot encode a difference of 2 using 1 bit, and so neither we can cover this edge nor can we cover that edge. So both edges are left uncovered, and therefore differential allocation is useless in this case, and that's why we have a cost of 2. Again, recall why we are not able to cover it. Let's go back to this particular diagram that we always have followed in terms of what we can and cannot encode as differences. So we can encode this difference of +1, +1, and +1 here. And so if we have to encode a difference from R2 to R1, for example, we have to go via 2 hops. And so the modulo or the D value here, the difference value is equal to 2, and that cannot be encoded. And similarly, if we have to encode the difference between R1 and R0, we have to go from R1 to R0 only following these arrows in this clockwise direction. And so we have to take 2 hops to go to R0 here. And again, a difference that is generated is 2. We cannot encode it using 1. And that's why both edges are left uncovered here. So now let us look at the heart of the problem. The heart of the problem is this transition going from R2 followed by R1 followed by R0. This is the worst case for this differential encoding. What if we change this register allocation so that the sequence of accesses changes? Maybe from R0 to R1 to R2, then everything could be covered. And let's see if we can do that. And so the remapping technique that we are going to look at here tries to change the sequence so that maximum part of it can be covered using differential encoding. In this case, if we keep R0 through R0, we don't change that mapping. That is what is shown here. We leave the node the way it is. However, what we do is a simple change. Change R1, which is allocated to a live range, give it, instead of giving it R1, give it R2. So now the node R1 is mapped onto a different node here, which was R2. So that is what is shown over here. So R2 becomes now R1. And then not only we do that, we also let R2 become R1, and that is what is shown over here. So in other words, R2 and R1 get swapped. So the range which was getting R1 as a register now gets R2 as the register, and the range which was getting R2 as a register now gets R1. So having seen the key idea, which is to change the sequence in a way that is maximally coverable by using differential encoding, let us look at an algorithm which actually does this. And the key idea is to do remapping, that is, shuffle the register numbers around assigned to live ranges so that the sequence appears to be implementable by including differential encoding in the register field. So here is the register vector that we have, that is the register numbers which go from N0 to a certain number. And then the idea is to create a shuffling or a permutation of these numbers so that different numbers get allocated to the ranges, and that changes the access graph or the adjacency graph that is we are using for the differential encoding. So the first step is to start with the existing register allocation that is there. Remember, we are doing this as a post-pass approach. That is, the registers have been allocated and all we are doing is shuffling them around so that we change the adjacency graph. So let's start with the initial vector assignment after the code is generated from the current allocation, and we try to find out its cost. That is, which of these edges are not covered by the differential encoding in the graph. Next thing we do is to pick a pair of elements in this register vector and swap them around, and to find out again the maximal cost of reduction by doing this swap. So now certain edges will get covered, certain other edges may not get covered because of the shuffling, and we find out the maximal reduction that we can get here. So you can see here that different swaps will generate different benefits or reductions, and we'll try to find out the maximum one that we can get here. In other words, we're trying to find out which are the two registers pairs that should be swapped around to get the maximal reduction. So at this step, we find out if there is a benefit in carrying out the reduction, and if it is yes, we carry out the swap. After carrying out the swap, we again go back and try another pair, and we keep iterating, trying to find pairs to be swapped around which have maximal benefits in each stage. And you can see that after a certain different kinds of swaps, anything further we try to improve will not lead to any reduction. The cost will in fact increase because certain edges will not be covered and so on, and therefore we'll terminate at that particular point, and that is how we'll carry out the remapping. So what I have here is an interference graph and an adjacency graph, and based on these I would like you to do different types of remappings. So the first question is, how many different assignment solutions are possible here, and then what is the largest cost of a solution, and the third one is what is the lowest cost of a solution. Please go ahead and mark your answers now. The second one is about the largest cost of any solution, that will be 2, and then the third one is what is the lowest cost for any solution, that is 0. So now let us look at the different algorithm which operates inside a register allocator. In particular, let us see how we can modify the differential select phase of a graph coloring allocator to do a different kind of allocation. So recall Briggs' algorithm. The nodes have gone on the stack during simplification stage, and during select stage they are being removed from the stack and assigned a color. At this stage is when we try to take advantage of these differential encoding. So what we do is, just like in Briggs' algorithm, we pop a virtual register from stack. Then during a color assignment stage, we insert it both into the interference graph and the adjacency graph that we are trying to construct. The adjacency graph and the interference graph in this particular case consist of those virtual registers that have been already given physical registers. So when we put this node back into both of these graphs, we recover the interference edges to the neighbors, and the adjacency edges to the neighbors in the adjacency graph, and we put those around this particular node. The next step that we do is we go to the interference graph to see which colors are available that are not used by the neighbors. If no available color is there, then obviously this is the case of spill, and we don't have to worry about differential encoding or otherwise, because this particular virtual register is not even getting a physical register. But if it is getting a register, and we could have a choice of multiple different colors, we look at all these choices here in step 4. And then for each of the allowed colors or register numbers, we find the extra cost that will be incurred if the edge is assigned with this given register number, especially in terms of the adjacency graph. So we'll find that if we have to give this particular color, it will lead to such and such transitions in the adjacency graph. And if we cannot cover those transitions, then there will be a cost associated with those. And that is the cost of this particular color. And then, obviously, we'll pick the one which has the minimal access cost, wherein most of the transitions to this particular color can be now covered by differential encoding. That is the particular motivation here, and that's why we picked the one which has the minimal cost. So what is the most important thing here that we are doing in this particular differential select modification of the Briggs coloring algorithm? Amongst different available colors, the one that covers maximum edge weights in the adjacency graph is the color that is picked in the select phase of the algorithm. So now we tried this framework with yet another scheme which is particularly attractive, which is Appel and George's optimal register allocation algorithm, which takes advantage of coalescing. What is coalescing? As you have seen in the earlier parts of this course, it is merging two subranges so that we can avoid register-to-register move. And based on this particular algorithm, we are going to see how to take advantage of this in light of differential encoding scheme that we introduced. First, let's take a look at differential coalescing scheme by Appel and George, which is a famous algorithm, which is optimal. So this generates spills optimally and also coalesces instructions very aggressively, and therefore a lot of problems about differential edge-based coverage could go away because of coalescing. We wanted to in fact see whether these kinds of schemes which do coalescing very aggressively can even take an advantage of differential encoding. So I refer you to the detailed paper which is in the instructions manual, which has given the details of how the coalescing is integrated with differential encoding. There are other key aspects which I would like to highlight here. One is more registers are exposed and used in this scheme, so the spills are significantly reduced in the optimal spill phase of this algorithm. And in fact, we tackle both coalescing and set last reg instruction in stage 2. So we have modified the coalescing stage, making it sensitive to the last reg instructions that are getting inserted. And the coalescing is now weighed with regard to this particular insertion of instructions. And then the second thing we did was to integrate the differential select mechanism, which we outlined earlier, to search for a solution which reduces last reg instructions as well in terms of different choices of colors. Let's go to this particular quiz to test our knowledge of coalescing. So the statement you have to fill in this here is as follows. Here the cost not only includes that for blank calculated from the adjacency graph, but also includes the cost eliminated due to blank removed. Please go ahead and fill in these two boxes. So in terms of this particular first box, the right answer is here the cost not only includes that for differential encoding, which is calculated from the adjacency graph, but the cost always of course includes all the moves that are eliminated because of the differential encoding. Finally, let us do what is the motivation behind differential register allocation through a quiz. So what I have here are 3 statements, and please check the one that is true. And the statements are: the main objective of differential register encoding scheme is to expose more hardware registers to the ISA and the compiler for improving the allocation and reducing the spills. or the second statement is to partition the registers into banks for allocation. And then the third one is to be able to implement more hardware registers for a given processor family. Please go ahead and mark your answers now. And the correct answer is, of course, the aim of differential encoding is really at an ISA level, to be able to expose more hardware registers to the ISA and the compiler for improving the allocation and reducing the spills. So differential register allocation is really an alternative to automatic register renaming, which is used in the hardware, which could be unpredictable, which could have a lot of expenses in terms of energy and costs and so on and performance. So by using differential encoding, whatever are the architected or hardware implemented registers, if they're all exposed to the compilers, then we can shift those costs from dynamic management to a static management, and therefore can have better energy and performance implications. Having seen how we modified the register allocations in 3 different ways, now let us see what are the other optimizations that this particular scheme could potentially benefit. One of the key optimizations that it has impact on is software pipelining. What is software pipelining? Simply put, it is scheduling of instructions inside loops so that it is maximally overlapping, and we do certain loop transformations such as unrolling to maximize these overlap opportunities. So one of the implications of software pipelining is that since multiple instructions are simultaneously live, which could have similar types of operands, it leads to a tremendous increase in register pressure. And this has been one of the bottlenecks to software pipelining in terms of the very high increase in register pressure and therefore limited opportunities to carry it out beyond a point. Why does this happen? Because we want to maximize this overlap, so we unroll the loops, and there is famous techniques like unroll and jam, and a lot of unrolling results in many instructions keeping the live ranges all clustered together, simultaneously overlapping with each other and simultaneously live, and that means higher register pressure. So in such a case, we apply differential remapping after the original register allocation is done. The first technique that we looked at earlier is what we apply here. Second application of differential encoding is to selectively enable differential encoding. For example, there may be high pressure areas where lots of registers are needed, and we could turn it on there to take advantage of this. And we could turn on and turn off differential encoding as per the register pressure to modulate the number of registers that are visible at certain points. So having seen the techniques, the integration, the different applications and advantages of doing it, let us see how it performs. We have evaluated this particular scheme through processor simulation. Again, remember, this has to be done by modifying the processor. So there are no existing processors which actually implement this scheme in hardware. So therefore, we had to use simulation. One kind of processors that we looked at are low-end processors or embedded processors, which have very tight budgets for operand fields. In such a case, what we did was we used the 5-stage in-order issue ARM thumb machine, and this machine has 16 physical registers and 3 bits in the register field. We tested 10 benchmarks from MyBench, which is a well-known benchmark in embedded systems available in open source. And then we modified the GCC compiler, put differential register allocation on top of iterated register allocation and optimal spill register allocation frameworks built in there. And the second kind of processor we looked at is high performance processor, which is a VLIW machine with 5-bit register field and 64 physical registers. And on this high-end processor, we executed a large number of loops from spec benchmarks. So here are some results of cost comparisons. The cost here means the cost of uncovered edges, for which we have to insert that select reg insert instruction. So you can see that there are different schemes here. This is the baseline, and this is the most optimal scheme. And the scheme substantially cuts down the spills here in terms of reduction in the cost of instructions for load stores as well as these additional insertions that we had to put in there. So you can see that there is the reason for this is quite easy to see. The total number of registers it allows us to use by using differential encoding using the same number of bits here is 12, whereas if you use direct encoding, we have only 8 registers possible here, and that's one of the big reasons, the increase in the number of available registers, which allows us to get rid of the spill cost. Here is the comparison of set last reg cost across 3 different schemes. You can see here that if we limit ourselves to remapping, this cost is significantly high, whereas for the other 2 schemes, this cost is much lower, as you can see through these bars. Again, if we compare the different schemes here, remapping is the largest code size increase, whereas select has almost no change, and the most optimal and coalesce actually reduce the code size, as you can see here. Now let us look at the most important number, which is the speed up over the version which does not take advantage of these differential encoding. There are speedups everywhere, that's the good news. Remapping gives a modest speedup of 4.5%. Integrating it inside a register allocator, which is brick style, gives you almost 10% speedup. And integrating it in the aggressive coalesce and optimal allocator of Appel and George gives you in fact 12% increase in terms of speedup. So you can see that the scheme benefits the register allocator at hand significantly, especially the Briggs allocator is benefited 9.7% and Appel's allocator is benefited 12% because of differential encoding schemes. And that's it. So what is the takeaway from this lesson? The takeaway from this lesson is through differential encoding, we can increase the available number of registers, and the register allocators, both graph coloring type as well as coalescing type, Appel and George's optimal allocator, can take advantage of it, leads to substantial speedups. The software pipelining is a major beneficiary of this as well. Please refer to the paper for detailed results. And therefore, such schemes are viable. And moreover, the hardware cost of doing it is trivial because all it costs is a very simple adder which is 4 or 5 or 7 bits wide. In this lesson, we learned what happens when we expose more registers to the compiler, how the instruction widths increase, how we can mitigate this problem by using differential encoding. We evaluated the benefits of differential encoding. We applied 3 different approaches at different stages of register allocators, and we found that they reduced spills and speeded up program execution.